Good evening. Today we are going to discuss the sample problem for week 3. So I am waiting for 2-3 minutes to others to join. Good evening. Today we will discuss some sample problem for week 3 classes that were taught in the course Thermodynamics Classical to Statistical, taught by Professor Sandeep Paul. I am Subham, EMRF, Department of Chemistry, IIT Guwahati. So we will wait for a few minutes and then we will start.
इसको हटा सकते हैं।
So we will start now. So today we are going to discuss week 3 problems. Some sample problem I have taken. So before starting that, I will start with the concept that were taught in the class. Just a brief discussion of the concepts, and I will start with just a beginning that were taught in week 1 and week 2 in week 3. So in week 1 we were taught about the first law of thermodynamics, about this heat and work. So we will start from there only. And then in week 2 entropy and second law, and in third week chemical potential and this fugacity. So let's start. We will start from first law of thermodynamics. So definition of it, that energy can neither be created nor be destroyed. It can only be changed from one form to other. So energy can neither be destroyed and it can neither be created. So it will change from one form to other. Like if we are doing some mechanical work and then mechanical energy will convert into heat energy or some other energy, like chemical energy change to heat energy and all. So the first law states that the energy can neither be created nor be destroyed. It can only be converted from one form to other, and mathematical form is du is equals to dq plus W, TW. Or this is for in small changes, for delta U is equals to Q plus W, where W is for pressure volume work, W is minus P external delta V. So now we will discuss about this heat and work done. Q and W. Q is energy transfer when there is a temperature difference. Like if there are two systems and they are having temperature T1 and T2, then heat can be transferred from T1 to T2, considering that this is not an adiabatic wall, so it can be transferred from one system to other. So energy transfer when there is a temperature difference, then it is known as heat, and it can be positive and negative. This is a sign convention for it. So when heat is transferred to the system, it is considered as positive. When heat is transferred from the system, then it is negative. Like if you can understand it by the exothermic and endothermic process. Exothermic process, heat is evolved and it is like delta H is positive for endothermic, and heat is given to the system, and negative for exothermic, heat is given by the system. So say similar goes here. Now work is energy transfer of energy when there is a difference in forces of two systems. To balance the force, what will happen? So same goes for it. It has positive and negative values. When the work is done on the system, it is considered as positive, and when the work is done by the system, it is considered as negative. When the work is done by the system, it is considered as negative. So this was all we studied about work and heat. Now we will talk about second law of thermodynamics. And it says that entropy of the system, entropy of the universe always increases. This means randomness or chaos in the universe always increases. For this randomness, delta, this S term is given, this is entropy and this is a state function. So delta S of universe is delta S of system plus surrounding. Like if this is the system that we are going to consider, and then rest everything left is, this is surrounding. So system plus surrounding will give us universe. So entropy of the universe is equals to change in entropy of the universe is equal to change in entropy of the system and change in energy of the universe, surrounding, and this is always greater than or equal to 0. Now some other quantity, like delta H is equal to delta U plus P delta V and this will be equal to delta U plus and delta NGRT, and delta Ng is the number of difference in number of mole of the gas between reactant and the product. This is known as enthalpy. U is internal energy. And other important quantities, like when volume is constant, what will happen? P delta V work done is equal to minus P external delta V, that will be equal to 0 because volume is 0. So delta U is equal to Q plus W, W is 0, so delta V is equal to Q. So at constant volume, internal energy is equals to QV. For delta H is equals to DH is equals to DU plus dPV, that is equals to dQ plus dW plus PdV plus PdV, VdP. This is the expansion of the formula. If we consider for both pressure and volume, none is constant, like initially. Now if pressure is constant, what will happen? VdP will be 0 and W will be minus PdV plus PdV, that comes from dQ, that will be equal to del dH, or we can say delta H is equals to, for major thing, delta H is equals to Q at constant pressure. So these two terms, enthalpy at constant pressure is QP and internal energy is QV at constant volume. So let's rub this, erase this, we will discuss some more points from the previous lectures. Now heat capacity. C. Amount of heat required to raise the temperature by 1 degree. So Cp and Cv, heat capacity at constant pressure, heat capacity at constant volume. Cp is equals to heat capacity at constant pressure divided by delta T. Cv is equals to heat capacity at constant volume divided by delta T. So this is heat capacity at constant pressure is delta H divided by delta T. This is delta U divided by delta T. From this we can also calculate delta H at constant pressure is equals to Cp delta T, delta U is equals to Cv delta T. Okay. Now after this we'll talk about some formulas of entropy. Of reversible processes. So we know, and we have discussed also, delta S is equals to N Cv ln T2 divided by T1 plus N R ln V2 divided by V1. This is also equals to N Cp ln T2 divided by T1 minus Nr ln P2 divided by P1. So in terms of volume and temperature, this is the formula. And in terms of pressure and temperature, this is the formula. So this can be reduced to other form with the given conditions. So we will study it for constant volume, constant temperature and constant pressure processes, isochoric, isobaric and isothermal processes. For isothermal reversible processes. So for isothermal processes, temperature T1 is equal to temperature T2, ln T2 divided by T1 will be equals to 0. ln 1 is 0, so ln T2 by T1 is 0. Formula will reduce to delta S is equals to Nr ln V2 divided by V1, that is also equals to minus Nr ln P2 divided by P1, or you can say Nr ln P1 divided by P2. This is for isothermal reversible process. For constant volume isochoric process, delta S will be equals to N Cv ln T2 by T1 plus Nr ln V2 by V1. Now V2 by V1 will be equals to 1 and ln1 will be equals to 0. So this all term is 0. So this will be n Cv ln T2 by T1. Now delta S for isobaric process, delta P is equal to 0. Constant pressure problems. Pressure is constant. Delta S will be NCP ln T2 divided by T1. Similarly, P2 is equals to P1 and then P2 by P1 is equals to 1. So ln1 is equals to 0. So the formula will reduce to NCP ln T2 by T1. So this formula we used for entropy. Let's see if someone trying those. Okay, so we'll move forward, and after that we talk about this state function and path function as well. And sorry, heat capable that delta S of transition at transition process A to B, delta S of transition will be equals to delta H of transition divided by temperature of transition. That is another formula. And state function and path function, the function which are exact differentiables are known as state functions, and this is the other way, which are not exact differentiables, or then they are path functions. And we can say that if we are going from A to B and we are going through this one path, and again we are going to A to B from this second path, if it is a state function, then this path 1 and path 2, that both will give the same values of that function, because it does not depend on the path that it is following. Let's say it is going from A to C and then D, then E and then B. So that property will be equals to the sum of, like 1 will be equals to sum of this step plus this step plus this step plus this step. So this is the state function. Like we can take an example of this internal energy. Let's say this is a state function. So if delta U, change in internal energy, sorry, delta U from A to B is delta U, then it will be equals to delta U1 plus delta U2 plus delta U3 plus delta U4. So delta U from going A to B will be equal to delta U1, delta U2, delta U3 plus delta U4. And how can we calculate that it is a state function or a path function? Then we need to calculate the exact differential. So these state functions are exact differentiables. So let f is a function, and we are differentiating it with respect to something x, and then again we are differentiating it with respect to y. Then it will be equals to curl x by curl y. If we first differentiate with y and then we differentiate with x, so both will be equal for state function. and for path function they are not equal. Not equals to path function. These values are not equal, so this is path function. Now we will quickly move to Maxwell's relations. So we discussed this Maxwell square in the last session. SPVT HGAU and then these arrows. So we can calculate DH is equals to DS dP. From S it is going to T, so it is TDS. So arrow is pointing towards T, so it is positive. From P it is going towards V, so it is VDP, and the arrow is towards V, so it is positive. For DG it is DP and DT, and from P it is going to V and arrow is towards V, so it is positive. And from T it is going towards S and arrow is pointing towards opposite to S, so it is minus S. DH DG dA is equals to dV dt. From T it is going to S and arrow is pointing opposite to S, so it is minus. From V it is going to P and arrow is pointing not pointing toward P, so it is minus P. Then du is equals to ds dV. From S it is going towards T and arrow is pointing towards C, so it is TDS. From V it is arrow is pointing toward V, not toward P. It is going to P and arrow is not pointing toward P, so it is minus P. So these are the Maxwell relations, and we can calculate some other relations from this as well. Like I can show one or two. Like at constant pressure, curl H dH by ds at constant pressure will be equals to TDS divided by T, and TDS divided by ds plus V dP divided by ds. Since pressure is constant, so this is 0, this is 0, so dH divided by 1, so it is T. And now let's apply this state function here. Let's differentiate with respect to P. Then we will get at constant entropy, then we will get curl T by curl S at constant, sorry, curl T by curl P at constant entropy. So we can calculate it in other way also, since we know that this enthalpy is a state function, so we can calculate curl square H by curl S curl P also. So these two functions should be equal. Curl square H curl P curl S. So these two should be equal. So let's calculate this. So what we need to do, we need to calculate curl H by curl P first at constant entropy. So at constant entropy ds will be 0, so this will be 0, and this will be this will be 0, and at this will be V only, so this is V. And again differentiating it with respect to entropy, we'll get curl T by curl S at constant pressure. So from equation 1 and equation 2, what we got? What we got? This curl T divided by curl P at constant entropy is equals to curl V by curl S at constant pressure. So like this we can calculate other relations as well from these 4 equations. These 4 are very useful in thermodynamics. So we'll quickly move to next part, that we taught in week 3 now. We'll move on to week 3 problem concept first. So let me quickly add some pages to write here. So now we will talk about Clapeyron equation. Clapeyron equation is dP divided by dt is equals to delta H of transition divided by T delta V. T is temperature at which transition is occurring. V is the delta V molar. So delta V molar is V at V2 minus V1. Like this is for, let's say, for evaporation, this will be volume of gas minus volume of liquid. And classic Clapeyron equation is ln P2 divided by P1 is equals to minus delta H of transition divided by R 1 over T2 minus 1 over T1. These two are very useful and we are going to use in questions. So in order to till now we were only discussing about the exchange of heat and work, Q and work, but we haven't considered the exchange of matter. So when we exchange the matter, then these some of these equations are not going to apply to the system. Then we need to calculate some partial molar quantity, partial molar property, like if there are n component in our system, for an n component system, let's say k component of system, and will make confusion with this number of moles. Here I will erase this and use this over. Let's say there are k component in a system and they will have n1, n2, n3 up to nk number of moles in those system in those components. So we say that Gibbs free, let's say we take Gibbs free energy first. We say that this is function of temperature and pressure, but this is for when there is not any exchange of the matter. So if there is an exchange of matter, then we can say that is the function of number of moles only, n1, n2 up to nk for k number of components. And partial molar quantity will be curl upon curl ni, curl G upon curl ni at constant temperature, pressure n number of moles of J, where J is not equal to I. We represent it is by bar over it. So this is partial molar Gibbs free energy. It is also known as chemical potential. Other we can calculate other partial molar quantities as well, like U bar, that is internal energy bar, is curl U by curl Ni at constant temperature volume, pressure volume, and number of moles. Similarly, other quantities can be calculated. Similarly, A bar, H bar, V bar, these can be calculated. V bar is nothing but curl V divided by curl Ni. Constant temperature, pressure, and J not equal to I. So these all can be calculated. Out of all these partial molar quantities, Gibbs free energy is the important, and it is known as chemical potential. We know we have taught in the classes that chemical potential of ith species is equals to mu naught I plus RT ln P divided by P naught. This is the formula for chemical potential of ith species. At equilibrium, chemical potential mu is constant everywhere, same value everywhere. So summation of mu I dni will be 0 at equilibrium. And there is a theorem, Gibbs-Duhem, which state that summation of ni d mu I is equals to 0. So this is very important relation as well. And let's say for 1 mole of pure substance, what will be U and G? They both are equal. Mu is equals to G for 1 mole of pure substance. So now we'll talk about G is equals to G star. I'll only writing these equations so that we can solve the questions. These are all discussed in the NPTEL lecture taught by sir, Sandeep Paul sir. RT ln F. What is this F? F is this fugacity. And fugacity is the measure of, this is the introduction of this real behavior in the of the system. So fugacity, it is very important quantity in thermodynamics. So there is a fugacity coefficient gamma. This can be stated as the ratio of fugacity divided by the pressure for pure component. This is for ideal and this is for real, and this is fugacity coefficient. Now another very important relation, ln of gamma is equals to z minus 1 divided by p dash dp integration from 0 to t. This is very important relation. And for v minus nb for n mole, one number of mole, p plus a by v square p minus b is equal to RT. ln f is equals to b divided by v minus b plus ln RT divided by v minus b minus 2 upon RTB. So if time permits, I'll solve this equation as well. I'll solve the expression to get this equation if time permits today. Otherwise, it is already been taught. So now let's start with the problems. I'll take a 2-minute break and then I'll start the problems for the week 3 tutorial. We are taking only 2 minutes break and then I'll start the problems. Okay, let's start again. So the question is that at what pressure will ice melt at -1 degree Celsius, assuming delta H of fusion is independent of pressure and is equals to 6.0095 kilojoule per mole, given the density of water and ice. Okay. So we are given density of water, that is equals to 0.9998 gram per centimeter cube, and density of ice is equals to 0.917 gram per centimeter cube. So we knew that this dp by dt is equals to delta H of transition, this is fusion, so fusion divided by T delta V. So we need V molar, we need this delta V molar. So for this we need the volume of this liquid water and this solid ice. So liquid and ice this. So let's calculate. We know that density is mass upon volume. So this will be, and we also know that for 1 mole of water mass is 18, H2O 16 plus 2 18. So for 1 mole mass is 18 and volume we can calculate from this formula now. So volume is 18 divided by 0.9998. This is per mole, like 18 gram, this is for 1 mole, gram per mole. So we can say that this is centimeter cube per mole. Centimeter cube is milliliter, milliliter per mole. For ice, this is V for liquid molar, this is volume for solid molar. So again for 1 mole mass is 18 and this is 0.917 and this will be centimeter cube per mole or ml per mole. So delta V molar will be equals to 18 divided by 0.9998 minus 18 divided by 0.917. So this is delta Vm. So I'll calculate it with calculator soon. 18 divided by 0.9998 is equals to 18.00. Okay, this is liquid minus, okay, for fusion liquid and okay, 18.0036 minus 18 divided by 0.917, this is 19.6292. So differentiating it, I am getting minus 1.6256. This is centimeter cube per mole. So what we got now? Delta Vm. So we have one quantity from this. So what other properties are given? Delta H is given. Okay, this is given, this is given, and we need to calculate the pressure. At what pressure? Pressure we need to calculate at which ice melt, and temperature is given. So we know that at pressure is equals to 1 atm, temperature of melting is 0 degree Celsius. Melting of ice is 0 degree Celsius. So at P1, T1, this is 273 Kelvin. And now we need to calculate P2, and temperature T2 is given, that is minus 1 degree Celsius, that is 272 Kelvin. So for this we need to integrate this equation, dp by dt. This can be written as dp delta h by delta v dt. So integrate it on both sides. Delta h by delta v, these are the constant for this with respect to temperature. So and it is given here also, from pressure P1 to pressure P2. This is going to have pressure T1 to temperature T2. So this will be P2 minus P1 is equals to delta H by delta V molar into, okay, this temperature is also here, dT by T. So ln T2 divided by T1. If we integrate dt by t, this will be ln T, and from limit T1 to T2, this will be ln T2 by T1. So what we are given, P2, okay, P2 we need to calculate, and T2 is given, that is 272 Kelvin. So P2 minus 1 atm, this is in atm, pressure 1, delta H is given, units is 6.0095 kilojoule per mole. So we need to take care these units as well. So I am writing it here so that we do not get confused. So now this delta V is minus 1.6256. This is centimeter cube per mole. Okay. So I have to erase this part. So now this we need to this like this is ln T2 by T1 also here. So we need to solve this equation and we will get the answer only. But the most important part is these units. We need to take care of the units while calculating, while solving this thermodynamics problem. We always need to see the units, because most of the mistakes we do there only. So okay. Now this is ln 272 divided by 273. So let's change this unit into first into joule. So it will be 10 to the power 3, and this will be joule only, joule per mole. Okay. And now this is in milliliter, and this is in joule. Joule, for this we need to convert it into this is joule is we can calculate like this. This energy is force into displacement, and force is mass into acceleration. So this units are kg meter per second square in meter square per second square. This is for joule, and so this is in meter square. So we have to take care these units. So for this I use R mostly. R. We know that R is 0.0821 liter atm per Kelvin per mole, and 8.314 joule per Kelvin per mole. So I'll use these two values of R to change the units. This is very easy to do. If I multiply it with 0.0821 and divide it by 8.314. So see, we are dividing R by R, but units are, we are changing units only. So this is liter atm per Kelvin, and this is joule per Kelvin per mole. So this is also per mole. So per mole to per mole will cancel out, per Kelvin cancel out. So this joule will cancel out this joule, and then this liter atm will remain only. So now we will get the desired units. We need atm and we need liter here. So for liter is decimeter cube. So we need to change this centimeter cube as well. So we need to multiply here only by, this is milliliter only. So 10 to the power minus 3. So now this is decimeter cube. Okay, I think you will get it. Like I have changed this centimeter cube into decimeter cube, and I use this R value to change this joule into liter ATM, so that we'll get a like the decimeter cube is what, liter only. So for getting the same unit in the formula and for calculating pressure in ATM, I have changed the units. Now you can see that per mole will cancel out per mole, and the liter will calculate liter, cancel out liter, then this ATM will remain only. So this is very simple way to change the units by using R. I mostly do it with R, so that I need not to know all the unit conversion for that. So now we quickly will calculate this values with calculator. So 6.0095. If you have any doubt, you can ask how to change this unit. I have changed unit. So if you have not understood, you can ask. So taking the log of 273, this is minus of this, and minus plus. Okay, and this 6.0095 into 0.0821 divided by 8.314 and 1.6256 into 10 to the power 6. So 1, 2, 3, 4, 5, 6. This is 133.97. So this is this will go up, and this is 10 to the power 6. So by calculating this, I am getting P2 minus 1 is equals to 133.97. So P2 is 134.97, and this is in ATM, atmospheric pressure. I have changed it here now, so liter ATM. So this is in ATM. I hope you understood this question. So what I taught basically here is this conversion of the units. Now the second question. This is a very simple problem. Calculate the free energy change, the compression of 1 mole of gas at 25 degrees Celsius from 20 to 200 atm, and the fugacity is given 18 and 120. So this is the pressure for this ideal gas, and this is for fugacity, that is for real. So this is what we are going to take here. So real. So delta G, we know that del G is equal to G star plus RT ln F2 divided by F1. Or we can say that this is ln F only. Okay, if we are calculating for G1, this is G1 star F1, and if we are calculating for G2, this is G2 star plus R2 ln F2. Okay, and for delta G will be from this, delta G is equal to G2 minus G1, that is equals to then this G star will be equal for both. G, this is standard. Yeah. Do you have any question? Do you have any question? Okay. My voice is coming clear or not? Oh, okay. Okay. So delta G is, sorry, okay, I have to take this pointer again. Delta G is RT ln F2 minus RT ln F1, that will be RT ln f2 divided by f1. So this is very simple one now. Delta G is equals to R is 8.314 into T is 25 degrees Celsius, that is 298 Kelvin. ln f2 is 120 and f1 is 18. So we can solve this and we can get the answer. So we'll use calculator, quickly calculate this. 120 divided by 18 and taking the log and then multiply it with 8.314 and 298. So I am getting 4700. This is in joule per mole. Okay, so this was a very simple problem. So we will move to next question. Yeah, this is a very interesting question, and this is from one of the GATE question. So maybe 2011 or 10. So ln gamma is this I have written in my early part also, that ln gamma is integration from 0 to p z minus 1 p dash dp. So at any temperature T, the fugacity coefficient is given by this relation, and where Z is compressibility factor, and the fugacity coefficient of a real gas governed by the equation of state P V minus B is equal to RT, where B is a constant given by this. So we need to calculate B. No, sorry. We need to calculate gamma, fugacity coefficient. Okay, and this is the relation we are given with. Two relation we are given with. This ln gamma is equals to integration from 0 to p z minus 1 divided by p dash dp dash, and other is this p v minus b is equal to RT. So PV minus PB is equals to RT. So PV is equals to RT plus PB. So this is PV, and we know Z is what, PV upon RT. So I am putting the value of PV here. Z is RT plus PB divided by RT. Okay, so this is RT divided by RT1 plus PB divided by RT. So this is Z. Now ln gamma will be integration from 0 to p z minus 1, that is 1 plus PB divided by RT minus 1 divided by P into dP. Let's say it is dP dash, since we are going to integrate it, so we need let's say dP dash, so P dash. So minus 1 plus 1 0, so this is P dash will cancel out this P dash, integration B upon RT dP dash from 0 to P. So it will be this will be Bp dash upon RT integration from 0 to limit from 0 to P. So it is Bp upon RT minus 0, that is Bp upon RT. So gamma will be exponential of this Bp upon RT. So the option D is correct. I hope you understood this question. We did, like, we expand this equation they have given, and we calculate the value of PV, and then we put this value PV in this formula of compressibility factor PV upon RT, and then we solve this ln gamma equation that we were given from 0 to P z minus 1 by P dash dP dash. So we get the answer Bp upon RT, and ln gamma is equal to Bp upon RT, and then taking the exponential, it is exponential of Bp upon RT. So now we will move to next question. At 100 degrees Celsius, the specific volume of water and the stream, specific volume, that is the key word. So specific volumes of water and stream are given, 1 centimeter cube and 1673 centimeter cubic, calculate the change in vapor pressure of the system by 1 degree change in temperature. So dt is given. The molar heat of vaporization of water in this range may be taken as 40584.8 joule per mole. So we are given this molar heat of vaporization, delta H of vaporization is given, delta T is given, that is 1. So we can consider it as Kelvin or degree Celsius, it is same only. So specific volumes are given, we need to calculate molar volume from that, and we can calculate delta Vm from there. So the formula is dP by dt delta HV by temperature at this transition is occurring, and delta Vm. So delta T we know 100 degrees Celsius, and delta T is 1, dP we need to calculate, and delta HV. So we are given most of the things, so we just need to change this specific volume into molar volume and calculate delta Vm. So first we will calculate delta Vm. So volume of water, liquid, molar less, like molar volume we need to calculate. So we are given 1 centimeter cube. This is for 1 gram. For 18 gram, like for 1 mole, it will be 18 centimeter cube per mole, because there are for 1 mole is 18 gram of water. So for if we need to calculate this 1 molar, then this 1 centimeter cubic will be 18 centimeter cubic per mole. So for similarly for the stream gas, we can calculate 1673, and we can this is in centimeter cube, and we can change into molar quantity by multiplying it with 18, and this will be centimeter cube per mole. So this is in milliliter per mole. If required, we will change it after in the formula only. So delta V molar is volume of gas minus volume of gas, molar minus volume of liquid. So this is 18 into 1673 minus 18. So this is 18 into 1672 centimeter cube per mole. I am not multiplying it, I will multiply all together in last by using the calculator. So this dP will be delta H, this dt will go that side, delta H 40584.8 by T is 100 degrees, so this is 373 Kelvin. Delta V is 18 into 1672, so this is Kelvin, this is joule per mole, so this is milliliter, centimeter cube is milliliter per mole. So we can change it into liter by multiplying it with 10 to the power minus 3. Okay, so now dt is 1, okay, Kelvin, okay, so Kelvin to Kelvin will cancel out, so 1 unit will cancel out, joule. So we need to convert this joule into liter ATM first. So again I will use this R for the conversion. I will multiply it with R and divide it with R, and I will use this liter ATM per Kelvin per molar, that is 0.0821 in multiply, and then 8.314 in divide. So 40584.8 into 0.0821 divided by 8.314. So this is 373, this is 18 into 1672, this is 1672, this is in liter per mole into 10 to the power 3, 10 to the power minus 3. So now this is in joule per Kelvin per mole, this is in liter ATM per Kelvin per mole. So Kelvin per mole will cancel cancel out, joule will cancel out, joule per mole, and this per mole will cancel this. So this liter will cancel out by this. So now we need to calculate this only. I'll use the calculator and calculate the value. 40584.8 into 0.0821 divided by 373 divided by 18 divided by 1672 and 8.314 into 1000. So the answer is 0.0357. 0.0357 ATM. We have reduced the unit to ATM. So dp is this. We can change it to any other unit as well. Let's say if we need to change it to mm of Hg, then we will multiply it with 760, then it is mm of Hg. So this is question number 4. So we'll move up to question number 5 now.
Sir,
Yes.
why you multiply and divide it with the different values of R?
Actually, your voice is not coming clear. Can you please write in the message box? Okay. Wait a minute. I'll explain this. I use it to change the units only. This is the simplest way to change the units. Okay. What you were saying? Which question you were saying? Okay, question number 4. Just give me a minute. So, like we need this. We are given in joule per mole, है ना? And joule is like this is energy. This is force into displacement. Then this unit of joule is kg meter square per second square. And we need in like our answer is in liter ATM. So I'll take other page here and like I'll rub this and explain here why I am changing this unit. Give me a minute only. This is a very simple way to convert the unit. Like, there will be very less means there will be very less mistakes in this, and we need not to learn this all the units, like remember all the units. So we know R is equals to 8.314 joule per Kelvin per mole, and this is also equals to 0.0821 liter ATM per Kelvin per mole, and also this is equals to 2 calorie per Kelvin per mole. Okay, so let's say I'm changing the I am given this pressure, and I'm changing it from this Newton to ATM. Okay, or let's say I'm changing this unit to this unit. Okay, so if I divide R by R, okay, then 8.31, I'm dividing it like this, 8.314 divided by 0.0, or in reverse order I'm doing it. So let's, sorry, zero point 0821 divided by 8.314. So this is liter ATM per mole per Kelvin, per mole per Kelvin, and this is joule per mole or per Kelvin. So per Kelvin will cancel out, per mole will cancel out. So this liter ATM and joule will remain only. Nah. So what we were doing here, this liter unit, this is liter is in decimeter cube, and we know this joule is, this is kg meter square. So meter square will involve here. So we need to convert these units now. So for solving this, for doing this, I am using this only. So this liter will appear here, and then this joule is cancelling out with this joule here. So this liter will remain only. I hope you understood this. This is only for conversion from one unit to other. R by R is equals to 1. So you can always convert one unit to other just by multiply with R and divide by R. Like if you want to change this joule into calorie, this is the unit of energy only. If you want to convert joule into calorie, so what I will do, this I will divide 2 by 8.314. So let's say I am given 1 joule. So I will multiply it with 2 and divide it with 8.314. So like this I can calculate it in calorie. This is joule per mole per Kelvin, and this is calorie per mole per Kelvin. So per mole per Kelvin will cancel out, and this calorie joule will cancel out with this joule, and this calorie will remain. Okay. Okay, I'll explain it again. This conversion of joule to liter ATM. I'll take one page and just show you the unit conversion only. Okay, I am converting 1 joule into liter ATM. So I know that R is 8.314 joule per Kelvin per mole, and also 0.0821 liter ATM per Kelvin per mole. Okay, so 1 joule. Okay. So now we'll move up to the 5th question. The vapor pressure of water at 95 degree is found to be 634 mm of Hg. And what will be vapor pressure at temperature 100 degrees? Molar heat of vaporization is given. So from Clausius-Clapeyron equation you can calculate this easily. as we know, ln P2 divided by P1 is equals to delta H, this is vaporization, so delta HV divided by T minus, sorry, R 1 over T2 minus 1 over T1. We are given P, what would be vaporizer temperature is, so P1 is given 634 mm of Hg, P2 we need to calculate, temperature T1 is given 95 degrees Celsius, so it is 368 Kelvin, and T2 is given, this is 100 degrees Celsius, this is 373 Kelvin. Okay, so we'll put the values and get the answer. ln P2 divided by 634 is equals to minus delta HV, that is 40593. R is, this is in joule per mole, so we will take 8.314, 1 over T2, T2 is 373, T1 is 368. So solving this, we will get this 368 minus 373, this is then minus minus plus, so 40593 into 5 divided by 8.314 into 373 into 368. So I will calculate this quickly. Four zero 593 into 5 divided by 8.314 divided by 373 368, taking the exponential and multiply with 634. This is 757 mm of Hg. P2 is 757 mm of Hg. 0.4. Okay. This is, I simply solve this part and then take the exponential of this and multiply it with 634. So I hope you got it. So I'll move to next question. Specific volume of ice and water are given. Specific volume again. So we need to calculate this in molar volume. What would be the change in melting of ice? Okay, per atm increase in pressure. So dP is given, dt we need to calculate. So dP by dt is equals to delta H upon T delta V. So dP is given, dt we need to calculate. T is 0 degree Celsius, so that is 273 Kelvin. So delta V, we will first calculate delta V. So volume of ice molar will be, we'll multiply it directly by 18. So 18 into, this is specific volume, so we need to multiply it with 1 mole, and 1 mole is 18 grams. So this is 18 into 1.0907 centimeter cube per mole. Volume of liquid is 18 into 1.0001 centimeter cube per mole. So delta V is equals to, it is converting from solid to liquid, so volume of liquid 18 into 1.0001 minus 18 into 1.0907, that is, so I will quickly calculate this. So differentiate this, taking the difference 1.63 minus 1.63 centimeter cube per mole. Okay, this is in milliliter per mole, so again we need to change it. I'll change it here only again. So dt, I'm splitting this T delta V by dP. Okay, dt into dP divided by delta H. So let's change it to liter, minus 1.63 into, this is milliliter, so 10 to the power minus 3 liter per mole. So here this is 0 degree Celsius, so 273 into minus of 1.63 into 10 to the power minus 3 liter per mole. dP is in 1 atm per atm, this is, no, so 1 atm. So this is 6009.9 joule per mole. Multiplying it with 0.0821 liter atm per mole per Kelvin and 8.314 joule per Kelvin per mole. So this will cancel out, so this joule will cancel out, and this per mole will cancel out, this liter will cancel out, this atm will cancel out. So all the units are balanced now. This is Kelvin, so dt will be in Kelvin only. So we need to balance the equation first. So we have done that. Now we need to calculate this quickly. 0.0821 divided by 8.314, this is into 6009 into 9, the quantity that is 59535, okay, and the quantity 273 into 1.63, okay, divided by 59.35, okay, answer. So it is coming 7.49 497. This is 7.5 only, so 7.5 into 10 to the power minus 3 Kelvin. So this is 0.0075 Kelvin minus. I think it is correct, so you can check it. So minus 0.0075. So now we move to next question. Calculate the fugacity of H2 at 100 degrees Celsius and 300 atm. Okay, and A, B and Vm are given. Okay, this is for van der Waals gas. So this is for P plus for 1 mole. Okay, so it is not given, like moles are not given, so it is per mole only. So P plus A by V square V minus B is equals to RT. So ln for this ln F is equals to I have written this formula in my previous slide as well. If I get the time, I'll solve the expression for this, but let's see, or I'll solve this expression in the next class. B divided by V minus B plus ln RT divided by V minus B minus 2A upon RTV. This is formula for ln F. F is fugacity, and this B and A are van der Waals gas constants, van der Waals equation that we are using here, A and B. So B divided by B is 0.0266 divided by, this is in all the units are same only, so we need not to change this. So I'm not changing the units, I'm not writing the units because B and B minus B both are in same unit. So 0.266 divided by B minus B. V is 0.119 minus, this is 1 molar, so we are taking N is 1, so 0.0266 minus ln, R is 8.314. No. So this volume is in decimeter cube, so we have to take this R as 0.0821 liter ATM per Kelvin per mole. Temperature is 100 degrees Celsius, so it is 373 divided by volume. Again this 0.119 minus 0.0266 minus 2 into A is 0.244 divided by R is 0.0821, temperature is 373, and this volume is 0.119. So we can calculate this. ln F is, I have this solved only, so I can write the values because it will take some time, so you can calculate it by yourself also. So this is 0.2879 minus, and this is plus 5.8, and this is minus 0.134. This all will be 5.95. So ln F is 5.95. So F is e to the power 5.95. That is this is 385.25. Okay, this is in ATM because we are taking this R as liter ATM per mole, so per mole per Kelvin, so it is coming in ATM. Let me confirm the answer. So it is 383.75. So this was very simple problem, but all we need to know is this formula, and this we can derive I think in next class. Maybe we can derive this, or maybe in the course sir has derived it. So let's, if you didn't get it, so we can derive it in next class. So this question is the following equation, these two equations are given. ln P vaporization of ice is given, and ln P of vaporization of water is given. Where P is in mm of Hg, and the temperature and pressure at triple point of water, we need to calculate the triple point temperature and pressure, and molar enthalpy of sublimation, vaporization, and fusion. So okay, we will start with calculating the temperature. As we know that at triple point this pressure and temperature is same for all the conversions. Like, let me draw this phase diagram for water. Temperature and pressure. So this is the triple point, we know. So here this pressure and temperature is constant. So at triple point, this pressure of vaporization of ice and pressure of vaporization of water, this will be equal. So equation 1 and equation 2 are equal. So we can write minus 6140.1 divided by T plus 24 is equals to minus 5432.8 divided by T plus 21.41. So separate this 6140.1 by T minus 5432.8 divided by T is equals to 24 minus 21.41. So T is equals to 6140.1 minus 5432.8 divided by this 24 minus 21.41. So this is, let's calculate it quickly. 6140.1 5432.8 divided by, this is 2.59. So this is 273.1 Kelvin. Okay, units are in Kelvin only, I guess. That's the price. So temperature is 273.1. So now we have temperature, so we can put this temperature in any of these equation, and we can calculate this pressure. So we can calculate both pressure and temperature from this equation. So ln P is equals to minus 6140.1 divided by temperature is 273.1 plus 24. So let's calculate this quickly. 6140.1 divided by 273.1. This is 22.48. 483 minus plus minus, this is minus, this is plus 24. So adding 24, I'm getting, this is 1.52. I'm taking the exponential. Okay. This is 4.7. E is 4.57. mm of H. The units are given. This is in mm of Hg. Okay. So now we need to calculate this. Heat of molar enthalpy of sublimation, vaporization, and fusion. So we know this, that this is nothing but delta ln P of vaporization. So converting ice from vapor, this is fusion. Sorry, sublimation. This is sublimation. So this is delta H of sublimation upon RT plus some integration constant I. So this is the equation, the original equation. So now we know this pressure, and we know delta H upon R. This is delta H upon R. Delta H sublimation upon R, this is given, and I use this. So you can calculate this delta H of sublimation from here. So let's erase this first. So from equation 1, delta H of sublimation upon R is equals to 6140.1. So delta H of sublimation is 6140.1 into, if we need it in joule per mole, then we can multiply this 8.314. So let's multiply it. 6140.1 into 8.314. This is 51048.8 joule per mole. We can say it is 51.049 kilojoule per mole. Okay, now second equation, this is vaporization of water to vapor. So delta H of vaporization upon R is equals to this 5432.8. 5432.8. From here, by multiplying with R, we can calculate delta H of vaporization. So this is equal to 5.32.8. 8.314. This is 45.17 kilojoule. So we know that enthalpy is a state function. So going from solid to liquid to gas, this is melting, this is vaporization, and this is sublimation. So this we can calculate that delta H of sublimation is equals to delta H of fusion plus delta H of vaporization. So delta H of fusion is delta H of fusion is delta H of vaporization, minus of delta H of vaporization plus of delta H of sublimation. So sublimation, delta H of sublimation is 51.049 kilojoule per mole, and for vaporization it is 45.17 per mole. So this is 978.5. So this is 5.879 kilojoule per mole. This is enthalpy of this fusion. Okay, enthalpy of fusion is 5.879. So we get all the property, I guess. So we now have temperature at triple point, pressure at triple point, and sublimation and vaporization fusion enthalpy. So we'll move to next question now. I'm taking 1 minute break for water only. So okay, let's start again. Question number 9. The vapor pressure of solid selenium is given. and liquid selenium and of liquid selenium by log P is equals to this, and triple point of the, so we have solved similar question. In last question was similar only. Log P, there are two equations are given of log P, and we know that at triple point pressure is this constant. So triple point is a point where pressure and temperature is same for all the states. So for these two states, this log P, we will equate this and calculate the answer. So let's do it quickly. So this is, let's say this is equation 1 and this is equation 2. I am equating both the equation, as we know that at triple point this is, or we have only one pressure and one temperature. So minus 7440 by T plus 12.78 is equals to minus 5390 upon T plus 8.63. So this is equals to 7440 upon T minus 5390 upon T equals to 12.78 minus 8.63. So this is 4.15. So T is equals to this 7440 5390, this is 0, this is 50 2. So temperature is 2050 divided by 4.15. So answer, let's calculate this quickly. 2050 divided by 4.15. This is okay. This is 493.98. Okay, 493.98. So answer we are getting in Kelvin, and the triple point we need to calculate this in degree Celsius. So in degree Celsius, this is 493.98 minus 273. So this is 220.98. So option 4 is correct. This was easy only. So let's calculate the next question. The fugacity of ammonia gas. We need to calculate fugacity of ammonia gas, and we are given with B at 25 degrees Celsius. Okay. So we have derived it in earlier question that gamma is equals to E exponential of Bp upon RT. We calculated in one of the questions, previous year GATE question. So this is the value of gamma, and we know that gamma is equals to fugacity upon pressure. So fugacity is pressure into gamma. Gamma is fugacity coefficient, and we are given pressure, true pressure, and we need to calculate only gamma, and we can calculate F. So gamma is equals to exponential of, since B is given, A was not given, so I have assumed that they are talking about PV minus B is equal to RT equation. So for this gamma is equal to this, and then from gamma we can calculate F. So exponential B 3.707 into 10 to the power minus 2 P pressure, okay, 10 atm divided by R 0.0821 into T is 298. Okay, so let's quickly do it. This is 0.3707 divided by 0.0821 divided by 298. Okay, and exponential, this is gamma is equals to 1.015. okay, and then F is equals to P 10 into 1.015, that is 10.15. Okay, option 1 is correct. So go to 11th question. Latent heat of fusion of deuterium का latent heat is given at this temperature, and the slope is this. The difference between molar volume of solid and liquid is, okay, we need to calculate difference in molar volume, and we know that dp by dt is equals to delta H upon this T delta V. So this is we are going to calculate. So delta V is equals to delta H upon T dp by dt, or dt by dp. Okay, so okay, latent heat slope dp by dt. Okay, dp by dt is given only, so this quantity we know, and everything is given, so we just need to solve it quickly. So delta V is equals to delta H. Delta H is 47 calorie per mole. Your wet temperature is 18.56 Kelvin. Okay, and then this dp by dt is 40.5 kg centimeter inverse square per mole. Okay, so we need to convert these into the units, so that we need. We know that dp pressure is into pressure in terms of this kg and centimeter is pressure is force upon area, so this is mass into acceleration upon area. So this is kg meter per second square divided by meter square, so this is kg meter inverse per second square. So this is the unit of pressure, and with this dp by dt should have the units of kg per meter per second square per Kelvin, but the unit given here kg, this is minus 2, so we need to convert it into minus 1 power. This times to the power minus 2, this is in this times to the power minus 1. So for that this hint is given here, so they have given g. Okay, so g is acceleration only, so if we multiply it with g, then it will convert into this. Okay, so we will multiply it with g, 9.8 meter per second square. In order to convert into unit, I have multiplied it with 9.8 meter per second. So since we know that pressure is nothing but mass into acceleration for here is gravity, this g, 9.8. Okay, so now problem is that this is in centimeter inverse square, so and this is in meter, so we have to take care of this also, and this unit, this is in calorie. Okay, so they have given to convert this is into joule, we need to multiply it with 4.184, or we we did earlier, we can multiply it with 8.314 and divide it by 2, then also this 4.184 will happen. So this is, since this is given, so I'll do it directly. 47 into 4.184, this is now in joule per mole. So joule per mole, joule is like we did earlier also, this is joule is kg mass into meter per second square into meter square per second square, so this is joule. Okay, now 18.56 Kelvin, 40.5 kg centimeter inverse per mole. Okay, let's convert this into meter, otherwise it will make confusion. So centimeter inverse square, and we are converting it into meter, so this will be 10 to the power 4. Since this is in inverse, so I multiply with 10 to the power 4. So this is 9.8 meter per second square. So I think now the units are even. So let's cancel out the units. kg per second square. This meter will make it meter inverse, and then will go up, this will go up, and then units are now in meter cube per mole. Okay, so let's quickly do it. And delta V. Okay, the answer we need in centimeter cube. So okay, we'll convert this again. So centimeter cube, this will be 10 to the power 6 into. So centimeter cube into all this. Let's quickly do this. 57 into 4.184 divided by 18.56, 40.5,
2.669, sir.
which one?
2.669.
Okay, so you are getting this 2.669. Okay, so delta V is equals to 2.669 centimeter cube per mole. That's what it is. Okay, so let's move to question number 12. Which of the following term is not zero when ideal gas are mixed together? So when ideal gases are mixed, this volume of mixing is 0, and this internal energy of mixing is 0, enthalpy of mixing is 0. We know that since there are no interaction between the particles, like if we are mixing A and B and there is no interaction between A and B, then there will be not any change in volume, there will be not any change in this internal energy and enthalpy. So only Gibbs free energy, change in Gibbs free energy will occur. And that's we do also, like with this formula, entropy and enthalpy only changes after mixing. That we know that formula, nRT summation xi ln xi. So after mixing, entropy of the this entropy and this Gibbs free energy of the mixer changes. So option delta H mixer no, delta V of mixer no, delta U mixer no, so delta G of mixer only changes. So this is, I think, second last question. Standard chemical potential of oxygen is given this, volume decreased through this isothermally, and increase in free energy is found to be this. The fugacity of oxygen is. So delta G, since we know that G is equal to G star plus RT ln F. Okay. Volume decreased to 2.46. I don't think we need this formula. Since we knew that G minus G star is equal to RT ln F. G star is nothing but the Gibbs free energy of real gas when fugacity is 1. So G minus G star is delta G. So delta G RT ln F. So this is 8.314 into T300 into ln F is, to calculate this. So delta G is 1.34 into 10 to the power 3 calorie. Okay, we need this in calorie, so this is 2. So ln F is 1.34 to 2000 divided by 2 divided by 300. I'm taking the exponential of it, 9.36. Okay, ln, so F is 9.36 is in ATM. This is 9.5 since we are taking expert approximation. This is 1.9 I think so. So this is 9.36. Okay. So last question. In the absence of any phase change, the change in entropy when a system is heated from temperature T1 to temperature T2 at constant pressure is given by. Okay, I have written it in my this discussion early that I was discussing the last topics as well. So delta S is, there is no any phase change, so this is for reversible process. This is NCP ln T2 by T1 minus N R ln P2 by P1. Okay, so at constant pressure this will be P2 by P1 is equal to 1, ln P is equal to 0, so that will be NCP ln T2 by T1. Okay, so this is the answer. I haven't written the option, so I don't know. So you can check it. This is the answer. I have solved these assignment question as well here. So thank you. This is from my side. If you have any problem, you have any doubt, you can ask, and you can ask in next class as well. Or I'll explain that one formula of that ln f. I'll explain the next class. So thank you. You can leave now. If you don't have any problem, you can leave now. Okay, thank you.